Alright, so we're trying to balance this formula. Since we have a 1 plus charged ion here and a 2 negative charged ion here, we need to be able to put them together, add them together in a way with coefficients in front of those so we can get a 0. So we need 2 of these, 1 of these, so that means I need 2 potassium ions and only 1 SO4. And I don't put 1s in front of it like I don't put 1s in front of X's or Y's, James. And so we need 2 potassiums. Now listen, when I bond 2 potassium ions to the sulfate, I show that bonding with subscripts. Alright, now we need to figure out what our products are going to be for this equation. So I have an ionic compound here. I have an ionic compound here. How do I know it's ionic? How did I know that? Metal and nonmetal. I have an ionic compound here. How did I know that was ionic? No, there's no metal, nonmetal. This is it has a polyatomic ion in it. The way you know you have an ionic compound is either it's a metal or nonmetal, or it contains a polyatomic ion. We have to look it up. We know there's a polyatomic ion there. Yes. 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 All right, so if I have 2 ionic compounds, what classification of equation is this going to be? More than likely double replacement. So the front part of this needs to go with the back part of that. Okay? And the front part of this needs to go with the back part of that one. Now I need to balance these formulas, but before I do that, I want to make sure I have a driving force for this reaction. Because if I don't have a driving force, we stop. Well, the first thing is, in the problem it says calcium chloride was dissolved in water. So do I need to look that up on the solubility rules? No, it already tells you it's dissolved. So I can say that's aqueous. Because I said it was dissolved.
Is that an S or a 5?
Where? Right here? This is an S. Sulfate. And it says potassium sulfate is dissolved in water. That's also aqueous. Okay? I need to know if calcium sulfate's aqueous or a solid. What are the 3 driving forces for a double replacement reaction?
A solid, a liquid, and a gas.
Solid, actually the liquid is water. Solid, water. That's good though. Solid, no. Listen, in a broader sense, the formation of a liquid is correct. But in this class, I've just taught you to look for water. Because almost all the liquids we're going to make will be water. Okay. We're never going to look for a different liquid in here. So the formation of a solid, formation of water, or the formation of a gas. And the only gas we'll have is when we make carbonic acid and we get a carbon dioxide evolution. Okay? And that doesn't happen very often. So, all right, so let's look up on our solubility rules. Everybody get their test references out if you don't have them out. Practice makes perfect. Test references. All right. Everybody, has everybody found sulfate on their test references? Okay, most sulfates are soluble. There are a few exceptions. So what is this going to be then? Solid, because calcium sulfate is one of the exceptions. Most sulfates would be soluble, but not calcium sulfate. That's what the exceptions mean. Okay? How about potassium chloride? What's it going to be? How do you know?
Because it says, except bromide and iodine.
For what? How do you know that? Somebody tell me how I know this is going to be aqueous, if that's correct.
Because on the solubility rules, solubility, we're saying all chloride, bromide, iodine. I know.
Okay. That's what I'm asking. I want you to read it out to me. Okay, good. It also says in the rule above that group 1 salts are always soluble, and that's a group 1 metal, so this is a group 1 salt. Okay? So both those rules apply to this one and say it's aqueous. All right, so do we have a driving force?
Yes,
Yes, we got the formation of a solid. All right, we need to balance the formulas now. Got to balance the formulas. All right, what is the charge we're going to assign to this calcium? Calcium is a 2 plus. We already have the charge on the sulfate. SO4, 2 negative. So do I need to do the math? Yeah, this is already 2 plus and 2 negative. We know this is going to be a 1-to-1 ratio. You should know by now. We've been doing this long enough. I hope you do. Okay. How about calcium and chloride? What ratio do we need of those? Both of them are, this is 1 positive, this is 1 negative. That's already balanced. Because the two, since the charges are the same, they balance each other out. Okay? All right, now we have to balance the equation. And what is the tool we use for balancing equations? AI, atom inventory. Calcium, chlorine, potassium, sulfur, oxygen. Make our grid. All right, got one calcium, 2 chlorines, 2 potassiums, 1 sulfur, 4 oxygens on the left side. On the right side, we've got 1 calcium, 1 chlorine, 1 potassium, 1 sulfur, and 4 oxygens. We always save oxygen for last. What do we want to balance first? Calcium's already balanced. Chlorine. So what do I put in front of this to give me 2 chlorines? Coefficient of 2. Remember, once the formulas are balanced, can't touch this. Okay? So that 2 in front of that means I can put a 2 here and a 2 here. That's how I'll add those up, and everything's balanced. Now we have what we need for the molar ratio we're going to have. Our starting amount is this answer we got in the last problem, 0.080, or 180, I'm sorry, moles of calcium chloride. And that goes over 1. And then from this balanced equation, I'm going to write a molar ratio. So this molar ratio comes from this balanced equation. Molar ratios come from the balanced equation. So I want to match the units and species in this step, this first step, match them down here. So we know we're going to have moles of calcium chloride down here. Okay. We know that we're going to need moles of the other species over on this side. Okay, so the other species we're looking for is what? Potassium sulfate, because we're looking for the other reactant in this problem. Okay, so I just need the coefficients in front of calcium chloride and potassium sulfate. What are those coefficients? 1 and 1. Well, that makes the math easy, doesn't it? 0.0180 moles. Cancel the units. Cancel species. And we know we have moles of K2SO4. Hey, I don't even have to round off. Okay? Alright. This then becomes a new starting amount again, because we're right here in our mole map up here, or our solution map up here. We currently have the moles of the ending reactant. Yes. Can we finish this first? Okay. What now? Slide it up. All right. So this amount then becomes a new starting amount, because we've got to get to the mass of that stuff. If I'm going to go from moles of this stuff to the ending mass, what do I have to get there? Molar mass. I need not only grams, but I need moles too. I need an equality statement that allows me to convert from moles to mass. So we need 2 potassiums. The formula has 2 potassiums. We need 1 sulfur and 4 oxygens. Okay. All right, so potassium, 39.0983.
What is that beside the zero? I can never. And I've been writing Q's and fours. What is that? Well, I can't tell what the. You know what? Everybody can tell your name. What's that? Oh, ew. No, thank you. You like. Whoa. Whoa. Ew, what did you over there? He rolling, so it's not creepy.
That boy.
I can't do the clap.
Folks.
Everything I do is out of control. I can't do the clap. Bless you. I love you. I heard this stuff up and up on the. Ew, no. This is better. We know where you got sick from. No, it's just. I covered up now.
I hear an awful lot of chatting that doesn't have anything to do with this chemistry. So that's kind of a problem because you need to know this stuff. Alright, we got one empty slot up here. So I have to round off that digit right there. Alright, Shane, this is going to be grams of K2SO4, but we can't just write that. We also have to say that it's equal to 1 mole of K2SO4. And once we have this equality statement here, then we have what we need to write the conversion unit to get from moles to grams. As always, the conversion unit has to have units and species that match what's still remaining up here. So we know whatever we're going to put down here has to be moles of K2SO4. And the side of the equality statement that has that shows 1 mole. The other side of the equality statement has 174.259 grams K2SO4. Okay? So now we're ready to do the math. We've got to cancel units and species. Units go away, species go away. Yep. Huh? You write the answers in your lab notebook. Well, let's get back to that in a minute, okay? Let me finish this problem. Okay. Well, not cross multiply, we simply multiply. Cross multiply is a different process. And we don't do cross multiplication in this class. Does everybody hear me? We should not be doing cross multiplication in this class.
Oh, it'd be divided.
Yeah, Amber.
Yes, it needs divided.
Alright, so that's grams of K2SO4. And we're going to underline everything but the first 3 digits because this number has 3 digits and this one has 6 and we don't care about the ones. Then we're going to underline everything after the first 3 digits and round it off. 3.14 grams of K2SO4. Now that is the amount of K2SO4 that would be used up if we were to completely react all of the calcium chloride. So Now that we have this number, we need to determine what our limiting reactant is. Okay, yes.
How do you know which one to round off?
What do you mean which one to round off?
Which number, like how you round it? Starting at 6?
Yeah, starting with the first 6 is where you round off. Huh?
How you know that?
Shh, please. The way we know that is this number here has 3 significant digits. Leading zeros are not significant. This number has 6 significant digits. These 2 numbers aren't used because they're counting numbers. So of this calculated number and this calculated number, this one has the least digits. So I choose to have 3 digits in the final answer. Okay? All right. The rule is, listen please, this is very important. I had you write it down yesterday, but looking at your homework, it doesn't seem like people got it. It's written in black and white, but you got to read. You got to read. Shh. Okay? The rule is, if this calculated amount of this reactant is greater than the given amount of this reactant, then that's the limiting reactant. Let's look and compare. How much were we given of that stuff? So is this calculated amount greater than the amount given? Therefore, 3 dots means therefore, K2SO4 is the limiting reactant. Or I could say equals the limiting reactant, I guess. That's fine. Okay? That is the limiting reactant. I can just write the word is, too. Is limiting reactant, LR. Okay? That's how you find the limiting reactant. Same stoichiometry, same mass and ass kinds of problems we've been doing. When we get to the end, we determine the limiting reactant.